let's just review a little bit about improper integral. I'm going to integrate this, and you guys try to catch my mistake. There will be an intentional mistake here. Number one, how do we integrate such a thing? And then don't be doing, oh, this is equal to ln of x squared plus x minus 6. What happens if you do such a thing? This gets you negative 10 points, right? You've been warned. That's not ln, okay? There's no way. Okay, so what is a proper way of doing this? Well, we are supposed to do it with partial fraction. You get it? Okay, so let's perform partial fraction. 1 over, and then distinct factors to x minus 2 and x plus 3a. I'm going to zoom in a little bit. So, and we're supposed to put a over x minus 2 plus b over x plus 3a. Do you have this ability to look at it and split this into partial fraction? What? Okay, tell your story. When I first came to Peninsula High, I started teaching calculus BC in my second year, so I didn't always teach this class, but I always taught multivariable calculus, advanced calculus class. And then on my first year, I never learned this technique really, because my high school teachers in Korea, you just look at it and figure out, yeah, 1/5 minus 1/5, and that's it. So I always did that. So I looked at it and say, okay, this 1/5 each, right? And the students were asking me, how do you do that? But I didn't understand. What their question meant was, how can you just look at it and split it up into partial fraction? They knew what partial fraction was. They are just a little amazed at my ability. But I took that as like, you kids don't know what partial fraction is? Like, how do you not know how to do that? How did you get here at this level? I mean, that look. And that was like awkward moment. And then years later, when I started teaching pre-calculus, I looked at the book and say, oh my God, that's what they do in this country, right? Okay, so, those kids were not idiots after all, huh? They're just asking me, how do you do that in my head? Sorry about that, guys, but they're long gone. They're grown-ups now, so I'm pretty sure they got over it. Okay, let's review partial fraction. You see how this test will turn out? All of the skills from chapter 6 and on, it gets piled up. So we find the common denominator. So 1 is equal to, here's a, and then multiply it upwards. So we have x plus 3 and plus b, and then x minus 2. Good. Now we choose an x value that is convenient for us. Let's say 2 first. Left-hand side is still 1, and right-hand side, this becomes 5a, and then this one dies. So that tells us a is 1/5, so I told you this is 1/5. And then if we choose x to be negative 3, then left-hand side is still 1, and this dies, and you have negative 5b. So that tells you b is equal to negative 1/5. You get it? Okay, then this thing, this integral right there, now try to catch my mistake. So my integral here from 0 to 5, 1 over, I'm going to put dx up here, and then x squared plus x minus 6 will be 1/5, this first one, this one. So we have dx over x minus 2 from 0 to 5 minus 1/5, because b is negative 1/5, and then 0 to 5 of dx over x plus 3. That is equal to 1/5, and that looks weird, 1/5 of ln, and this time we are sure this is ln, and 0 to 5 minus 1/5 and ln, and we are sure about that one too. And then 0 to 5. Seeing my mistake yet? substitute 5, so ln 3 minus substitute 0, so we have ln 2 minus 1/5 of substitute 5, so we have ln 8 minus substitute 0, ln 3. What is wrong with this? Yeah, I see a hand. Wait, whose hand is it? Matthew.
It's me. I'm not entirely sure about this, but is it something to do with the absolute values of the ln?
No. Because antiderivative of 1/x is absolute value, right? Okay, Ryan.
The limits are 0 to 5, but you can't put 2 into the first one.
You see the problem? 0 to 5. In between, there's a vertical asymptote. Sneaky little problem now, isn't it? So all of this flows up. This side is no good. This one is fine. Well, this one has a vertical asymptote too, but that's at -3, and then from 0 to 5, no problem. This is a well-behaved function. But remember when I proved the fundamental theorem of calculus, I told you that condition, you have to meet this one condition, and the condition being, it has to be a well-behaved function. And having a vertical asymptote, many times called singularity, is about the worst behavior of a function. I'm going to show you what this thing looks like. This thing looks like this. Put it right there. And we found out from here and on itself, this looks like 1/x. That itself is infinity. And this right there will turn out to be infinity as well. So we have like double infinity. And on both ends. So this is a sneaky improper integral hiding in a plain sight. And this could happen. It's your responsibility to identify the vertical asymptote and split this up. You know what I'm saying? So let me show you how to do this part properly. Okay, this integral, this one. Okay, this one is fine. You can just do that. So let me show you that side. Okay, so integral of dx and then x minus 2 from 0 to 5, you must split it up into limit, let's say a approaching 2 from the left hand side, and put a here, no, not a there, 0 to a, and then dx over x minus 2. You get it? And plus limit of b approaching 2 from the right hand side, and from b to 5 of dx over x minus 2. Okay? So what we are doing here is, let's go back to the picture. One side, you're approaching this vertical asymptote from the left-hand side, that's A, and B is approaching the other integral from the right-hand side, right? So two separate integrals are in here. You get it? Now, then we can just evaluate. So limit A approaching 2 from the left-hand side, and this is ln, and we are still sure from 0 to a plus limit b approaching 2 from the right hand side, and ln and x minus 2 from b to 5. So far so good. We substitute, so we have limit of a approaching 2 from the left hand side, so ln a minus 2, and then we substitute 0, so we have ln 2 plus limit b approaching 2 from the right hand side, substitute 5, so we have ln 3 minus ln, and then we have b minus 2. Y'all with me so far? Good. If you have a question, now would be a really good time. Now we're going to take the limit. I'm going to do it the long way. You can skip this line. So this of ln a minus 2, and this thing does not have any a in it, so it's just ln 2. And this one plus, this does not have b in it, so we have ln 3, and then minus is limit of b approaching 2 from the right hand side of ln of b minus 2. Here's our dilemma. Dilemma is these two combine in the middle, right? That's just ln 3 over 2. Can you combine these two? If we don't, this will turn out to be negative infinity, right? And this one is plus just ln 3 over 2. And that will turn out to be positive infinity. Do infinities cancel? Before you say answer that question, let's take a look at the picture one more time. They are both infinities, but they are exactly identical. Is there any way we can combine these two and cancel? One idea I had is this. Limit of a approaching 2, no plus, no minus, and just write that, ln and a minus 2. And then this one, negative sign, instead of b, just convert it into a. How about that? Oh, that's 1. ln 1 is 0, so they cancel and give you 0. That's great, right? No, you can't do that. Do you know why you cannot do that? Why not? One is left from left limit, and yet one is approaching to from the left hand side, the other is approaching it from the right hand side. Can't just convert it because this function may look different. So no, okay, fine, scratch that dot. Well, then this, how about this? Put that back and then write b minus 2 here. See what I wish that mathematicians created, double limit. Would that be nice, right? No, they haven't invented that thing. So forget this. Like this whole thing, we have to scratch that dot. There's no such thing. Well, then what? I've been struggling with this for years. And I have a story to tell you. So I ended up calling this math professor at Stanford. What? How do you know math professor at Stanford? No, I'm not that well connected. See, there are some 10th graders in here too, right? So those of you 10th graders, if you take this class in 10th grade, you take multivariable next year, then you run out of math classes to take. So what do? Do you know what you take? You take online linear algebra class, which is the next course in sequence from Stanford, the Stanford University. Oh, how nice, right? Oh, that'll look awesome on your transcript. And you also get high school credit. I mean, not that you need it, but hey, you need to have this on your transcript. Otherwise, so many serious universities will not consider your application. I mean, that's one of the rules. You have to have 4 years of math. So in order to meet that requirement, actually, you take this class. This is like a lot bigger than AP ever will be, because this is Stanford, okay? And I happen to be the coordinator of that program. See, they email me the test, and I give it to them, and I scan it back and email it back to Stanford. So I've been doing that. So I have this, each year that contact professor changes. 1 year, because this question is just bugging me too much, so I made an excuse to call the professor instead of emailing him and say, yeah, when you get the grade, could you send me the grade for our internal record? Because we have to create transcript here, so it's not that I really needed it, but I wanted to talk to this guy, okay? So yeah, of course, right? And then I said, while I have you on the line, could I ask you a math question? Sneaky, huh? And then he says, yeah, sure, of course. What do you have? Then I asked this very question. Do they, because they are exactly identical area, right? Let's just look at this much compared to that much. They are exactly identical, but they are both infinities. I know the infinities usually don't cancel, but in this case, can we cancel it or not? Right? And he said, no, you cannot. And the reason being, it really depends on the speed of this limit and A and B approaching that vertical asymptote. Whichever, because we cannot assume they are moving at the same speed. That's why you cannot have double limit. And whichever gets there first will win, and we have no indicator on which one moves faster. Like, you're kidding me, right? Who thinks like that? Who cares how fast these things move? Is that, I mean, as a mathematician, sometimes they can be crazy. Man, these guys are nuts, right? So I'm thinking, okay. No, you don't understand. I'm a high school teacher. Okay, so what do I tell the students to put down, right? I mean, it's for all the purposes of physics and engineering, they cancel. But in mathematics, pure mathematics, he meant, we cannot really assume such. Okay, fine. Let me rephrase my question. My students will have to take AP exam. All the graders are high school math teachers. Can you imagine if they say it depends on the limit of the A and limit of B, and which you think anybody will understand what they mean? So what the hell do they put down as an answer on their AP exam in high school AP exam? Can you answer that question for me? So he said, oh, in that case, and here's the answer. Ready? You just put divergent. I mean, this could be anything between negative infinity to positive infinity, literally. We just don't have enough information. So we just, when one of the two, so in summary, one of the two integral turns out to be infinity, even if you have something that potentially offset that infinity, we still put down divergent. You don't even have to bother with the other one. How about that? Good? Yeah, that was extra long question, unnecessary. Okay, now let's talk about comparison test. Okay, suppose we have this. Actually, I'm gonna start here. Say we have this integral right there. 1 to infinity of dx over 1 plus x squared. We actually know how to evaluate this integral. I mean, this is a headache, but do you see this thing becomes inverse tangent? This will turn out to be pi over 4. You want me to show you how to do that as a review? Okay, enough of you are nodding your head, so I have to say that for video purpose, because otherwise I sound like an idiot talking to the screen by himself. You know what I'm saying? This is a live class for those of you watching this video. I have students here. Okay, so for something like that, let's just calculate figure out the antiderivative first. I'm going to do it here on the side. So dx 1 plus x squared. This is very similar to the homework problem with it, isn't it? X is tangent theta and trig sub. So we have dx being secant squared theta, d theta, and 1 plus x squared also turns out to be 1 plus tangent squared, which is secant squared. So we have this thingy over this thingy. So we'll have d theta, and that turns out to be theta plus c, and theta, of course, is from here inverse tangent of x plus c. You get it? So we plug that in here, but we are supposed to rewrite this into proper integral. Remember that? So we'll convert that and put 1 to b and dx over 1 plus x squared. So far so good? Then here I'm gonna write down this work. So this thing turns out to be inverse tangent of x from 1 to b. Good? Then substitute, so we have limit of b approaching infinity of inverse tangent of b minus inverse tangent of 1. Okay, we did this in problem 23, right? This tangent, inverse tangent infinity is pi over 4, and inverse tangent of 1 is pi over, whoa, I screwed up, pi over 2, and this is pi over 4, so we get pi over 4. Or approximately 3/4, right? Pi being 3.14. So approximately 3/4. But that's not the point here. What happens if this thing is like 1 plus x to the 5th power? Then what are you going to do? Now we don't know how to integrate this thing, and it ain't ln. So the whole point is this, that infinity doesn't look pretty enough. So here is the scheme. Comparison test. Comparison test is, let's see if you agree with this. Do you agree with this statement? Is it true? At least between 1 to infinity, positive numbers. I mean, this thing doesn't care because x is being squares, it's always true. But some functions might not be true. So, but from 1 to infinity, I have reduced the denominator by 1, right? So this whole fraction is slightly bigger than that whole fraction. Do you agree with that? Either you agree or you don't agree. Give me an indicator. Somebody doesn't agree. I don't want to name names, but why don't you agree?
I mean, isn't that essentially saying infinity infinity plus 1 is greater than infinity?
No, it's not infinity, because when what we mean by improper limit is actually an improper integral is we put limit, and this is not infinity. As you can see, it's pi over 4. Ooh.
Oh, and if you evaluate the other one, it's going to be like,
this will be 1.
It's going to
I'm about to
1,
show.
yeah.
So the statement is pi over 4 is less than or equal to 1. See, that's true. Because if you graph most of the functions, this function is slightly higher than this function from 1 through infinity. So this is slightly greater area than this, is what we are getting at. You get it now?
Okay, that makes sense. Yeah, that makes sense now.
Okay, now, so we have found sometimes we don't need to know exact value of this integral. We just want to know whether this is convergent or not. Is it infinity or is it finite number? If it's finite number, we want to know what the upper bound of this thing is. And this integral will provide us with that upper bound. Now, so this side, we turn it into proper integral now. So 1 through b, and then I'm going to rewrite it like this. Good. Then b approaching infinity of, this is x to the -1, therefore negative here, right? With me? Okay. Limit b approaching infinity. And should we use plumbing, professor? So we have this one minus that one, right? With a negative sign. So we have 1 minus 1 over b. And when you take the limit, this 1 over b dies. So what we have is 1. So what do you have here? This integral, which just happens to be pi over 4, is less than or equal to 1. So this given integral is convergent. You get it? And upper bound is 1. Remember, this is about 3/4. That's amazing, isn't it? However, be careful in logic of the infinities. Let me give you another example. Say we have something like this. From 2 to infinity. Let's put x to the, what do you want to put? Not just x minus 1. Oh no, actually we can integrate that. So x to the 5th minus 1, so that we cannot really integrate it now. And then we can, no, that's a bad example. I'm going to just do this x minus 1, okay, for the sake of this argument. And then if I say this is same as dx over x, isn't it? Which is greater? It's this way now, isn't it? I'm gonna change that. Actually, I will do what we did. I'll just put X. I'll go back to my original. Okay. And then X to the fifths. I'll just stick with this example. I think this is a better example. Oh, I meant -1. Now, do you see why I started this with 2 instead of 1? Because if I put 1 in, there's a vertical asymptote on this end, so I have improper on both sides. I just want to deal with this one headache. I don't want to have to deal with two-sided improper integral. You know what I'm saying? So I'm taking that vertical asymptote out of the equation just to demonstrate the purpose here. So for circles, so I have made the denominator bigger, so this entire fraction is smaller. Do you agree with this assessment? Okay, but if we do this, limit of b approaching infinity, so from 2 to b, and the same thing is x to the -5th power dx, correct? b approaching infinity of, this is the x to the -4, so still for -1/4 here. You with me? Okay. Using plumbing professor again. So if you plug in 4, what is that thing? I mean, plug in 2, 6, 64? Do I have 64? Somebody check my algebra. This is too much algebra. And then -1/4 b to the 4th power. Good. And then this thing dies, right? So this thing dies. So wow, great, right? So what we get is 1/64. What have we concluded here? What can we conclude about this integral here?
That it is greater than 1/64.
So is it convergent or not?
It's divergent, or it's way.
So we know nothing, right?
Yeah.
Greater than 1/64 means nothing, because that greater than includes all the way to infinity. It could be 1, it could be 2, it could be 3, it could be infinity. That's a problem, right? So this is a logical flaw. You have to think about this direction of infinity and which is greater, right? And similarly, if you have something like this, say dx, not that we don't know how to integrate this from 1 to infinity, and this is true, right? But then we did this. This turns out to be infinity, right? Can we conclude that this is divergent as well? I mean, it turns out to be divergent, but no, you can't. Because less than infinity includes finite numbers, all of it. So these are meaningless conclusions. So you have to be careful about direction of these infinities. You know what I'm saying? So I'll go back to that example. So if we have such a thing, so 2 to infinity, what was it? X to the 5th -1. Right, we don't wanna, I have a great idea. See something about this distance learning? Only one good thing about distance learning is I get to do this, so I don't have to rewrite it and you don't have to watch it and rewrite the same thing in my boredom. Okay, so we cannot make that, but this is a valuable work we have done. You know what I'm saying? So once that happens, we do what's called the limit comparison test. And let me show you what the limit comparison test looks like. Go back up there, I zoomed in too much. This is what limit comparison test looks like. Does that look familiar to you? That sure looks like growth rate comparison now, doesn't it? Yeah, this is what it is. Which function grows faster kind of thing. However, it gives you the conclusion about the convergence of the integral as well. So let's learn how to take limit comparison test. Going down here, I think I'm gonna enlarge this thing slightly because I'm writing too tiny. Okay. So don't put any inequality here because inequality is the other way, it doesn't hold. What we just do is this, take a limit as x approaching infinity of our given function, which is this, over the function that you want to compare it to, this thing, 1 over x to the 5th power. That's ugly. Now, how do you find this function to compare it to? Easy, you just remove that 1, because if without that 1, you know how to integrate. You know what I'm saying? Say yes. Okay then. So this thingy will turn out to be, of course, limit of x approaching infinity of x to the 5th power over x to the 5th minus 1, isn't it? Do you want me to L'Hospitalize it, or do we know this is 1? This is 1, right? What that tells you is this integral and this integral, they're about the same ratio. This is almost 1 over 64-ish. You know what I'm saying? So when this thing gives you a finite number, either they both converge or both diverge. Huh. See, say this thing turns out to be 2. That means if this is 1 over 64, this is about 1 over 32. But you see why? Now do you see the motivation of defining growth rate the way they do? Because we want to compare the convergence of the integral to the infinity. That's the one that counts, not that which function is slightly greater than other function. We don't care. They are about the same kind of infinity, or in this case, same kind of finite number. Okay, so here's a trade-off. Limit comparison test works either way, regardless of the direction of inequality. So it's less thinking, it always works, or as long as you can find this function to integrate, and that's so easy, you just remove that thingy. Or just put the leading term and then integrate. It'll always work and give you finite number. But it's more work, because you have to do this and possibly L'Hospitalize it. Where the direct comparison test is a lot less work, but you have to be correct in your logic, and it does not always work. It works half of the time, and you have to think about it. You have to make sure that you got this inequality correctly. So use whichever the one is convenient to you. It's a judgment call. Unfortunately, this limit comparison test is not in our book, but AP has brought this back, so I always have taught it. It's important enough. And then I will take either one. AP will also take either one. Okay. Do you have any questions?
Wait, so it is possible to not get an answer with the direct comparison?
Mm-hmm.
Or it always can get you an answer if there
see, this
is
case,
an answer.
it's nothing, right? Let's just take a look
Yeah.
at this case that it gives you meaningless answer. It's just you conclude nothing out of this.
Oh, yeah.
So this is the case, the direct comparison test fails.
Okay. Then how about limit comparison? Does it always work, or there's still some cases that it doesn't?
It always works as long as you find the right function to compare it with.
And there's always a right function to compare with.
Most of the time. Let's not say always, because this, in case of polynomial, there's always one, because you just take the leading. You know what I'm saying? And that's integratable. If it's some kind of weird
Okay.
function that we don't know how to integrate, then we still have a problem.
Oh, wait. So if it's polynomial, do we just take the leading term, or we delete a constant? Like,
just leading term.
okay.
Because
Okay, so if I have like 3, 4 terms, we just take the highest power.
yeah, because that, and then you can
Okay.
see why that will give you a finite number here and this limit. And that's what we are getting.
Yeah.
Okay, if this thing gives you infinity or 0, then you have chosen your function poorly. So always choose the one that gives you preferably 1, but 2, 3, whatever, any constant will do. And it's easy. In case polynomial, just take the leading term and that will just guarantee to give you 1.
Yeah, okay. And will the will you or the homework or the test give us anything like they are both divergent? Like you don't get the after limit comparison test, you get like a infinite value.
If this is infinity and
negative.
limit comparison test gives you finite number, then that's infinity as well. They converge together or they diverge together. That's the whole point of it. You get it?
Oh, okay. Okay.
So this is a lot.
So the converse also work, right?
Yeah.
The converse of the comparison, like
yeah,
if they are both. Oh, okay, that also works. Okay.
Oh, actually, no, I take that back. Converse is not necessarily true. Because one could have fifth power in the denominator. This could have fourth power in the denominator. They are both convergent, but limit comparison test will not give you nice constant.
Oh, so but that's in a scenario we pick the wrong equation, right? Or
yeah, but you don't want to compare it to something like that. At least keep the leading term the same. You want the same degree of polynomial, then it'll always work.
Okay, and the converse will. Okay, thank you.
Okay. See, on Dropbox note, see, if you wanted to do this, there's a vertical asymptote right here in the middle. So you have to break this up into 2 separate integrals. That's a lot of work, especially with the limit, right? So what I decided to do was this. This is not exactly what is in the Dropbox note, but what I did was 2 times limit of from a to 1 and a approaching 0 from the right hand side is what I did, right? And then now Reese wanted to do the left hand side. So this is the side that we want to do. Well, then we have to change that to negative, right? Now, and then change this to -1 and a, like that, eh? Now, but in order to integrate, we have to do something about this thingy. What is the absolute value of x if x is negative in piecewise function? That. You see why most people want to go with a positive side? Because this potentially complicates our life, right? You still want me to go ahead and finish this up, or do you want to go back to the positive side? I mean,
that was my mistake.
Oh, okay. So does anybody want to see how this one is done? Or does anybody want to change it back to the previous one?
Can you go back to positives, please?
Yeah, because I guess you have to think about the reverse chain rule, okay, when you integrate. So let's not do that, because this creates like potential for mistakes. So let's go back, bunch of undos. What did I do? Okay, now we're back. So we'll take this back and we are doing this side, okay? By the way, this doubling and doing this work, well, like this better be convergent, right? Otherwise, double the infinity is still infinity. I mean, we always go down to that rabbit hole if something is divergent, okay? Divergence is a problem. Okay, so let's do this. That looks ugly. Dx, okay. Now, then we have to think about, wow, do we even know how to integrate this? By the way, we don't need the absolute value anymore because x is positive now. So ln x, let's just integrate ln x, shall we? Do you want me to do it here on a separately as an antiderivative, or do you want me to just do an integration by part? Also your choice. Many times, something like this, we need the integration by part. I do that on the side and substitute.
Can we do the integration by parts?
I know, but separately or just here? This one is not that bad. Okay, just do it and you'll know what I mean. So u is ln x, and then dv is dx, and then du becomes 1 over x dx, and v becomes x, right? So the two limit a approaching 0, and then what we have is these two, so x ln x, and then we have to write this thingy. This is the only thing that's pain in the butt. You know what I'm saying? And then minus the integral of these two, which cancel, right? So it's just dx from a to 1. Good. If we have done it on a side, then we don't have to write this. It's just like, it's about same amount of writing, so I just do it this way. I already started, so I'm committed now. So 2 limit a approaching 0 from the right hand side. This is x, ln x, and this becomes minus x. Now I can write it here, a to 1. You get it? And then now we have to wonder about what this limit is, right? So, well, I have to substitute first. So limit a approaching 0. Substitute 1, ln 1 is 0, so that goes away. So we have negative 1, and then minus a, ln a, and then plus a, okay? Are we good? Say yes. I see a little mistake on my Dropbox note. I put minus sign here. Okay, now what is this limit? That's the only thing, right? Because a approaches 0 and ln approaches negative infinity. So this is infinity over infinity idea now, right? So let's do that on a side. So limit of a approaching 0 of a times ln a, right? Okay, that is same as limit a approaching 0 of ln a over a to the negative 1a. So now let's check. If a approaches 0, this thing approaches infinity, ln approaches infinity. So we have infinity over infinity. Now we can L'Hospitalize this. So limit a approaching 0, and then this becomes 1 over a, and this becomes negative a, negative 2 power a. Say yes. And this is 1 over a squared, so simplifying fraction. So the whole thing gives you limit of negative a approaching 0, a. Am I saying a too many times, a? And that's 0. So this thing becomes 0, a. I don't know where I picked up this Canadian thing. I mean, I've been to Canada briefly on business trip only twice. I mean, I never went there as a tourist. It's like somehow I speak like Canadians. Actually, I didn't know, even though this was Canadian thing, until one of my students who's from Canada told me, like, hey, you speak like Canadian. Really? This is how they speak? Yeah. Okay. Okay, so a approaches 0, so this is equal, this goes to 0 too. Oh, wow, this computer is very unstable. I'm telling you. This approaches 0, so we have negative 2. Which is exactly what we expect, right? This is negative inside under the x-axis. Good. Okay, let's do 43. Okay, 43. The question was, how do I know which one to compare it to? Was it? Okay, first of all, this is very even function. If I replace x with a negative x, then you get exactly the same thing, right? Okay, so I'm gonna say this is equal to 2 times, and then from 0 to infinity of dx over e to the x plus e to the negative x. And then we do know how to integrate this thing, because I think I did it in the class once. Multiply e to the x here, 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 and then it becomes inverse tangent. But that's not the point. We want to use comparison test, right? Okay, then which one do we pick? Either we erase this or we erase this. Suppose we erase this, okay? Just suppose this is not right, so it's not going to work. Don't write it. So we have 2 limit of b approaching infinity of, if I cover this up and just have that, then we have this, right? Do you agree? Denominator. Now, this thing diverges to infinity, doesn't it? This function looks like this. And then this area, right? So eventually what we get is this. Now, what have we concluded? Nothing.
Nothing.
Right? You see the flaw of logic? This entire integral is less than or equal to infinity. You see why you don't want to do that one? So you have to pick the one that works, right? We want this to be a finite number, right? So the other one, this thingy, matters a lot. So we cover this up, right? So the correct way is you want to put that negative sign right there. And it's all downhill from here. Then we will integrate. So this is now equal to, see, if I put equal sign down here, same as continuing up, you know what I'm saying? So when to use equal sign, when to use inequality. This is a very standard practice in all math books in college, okay? Inequality there, equal sign. And if I have another inequality there, that's same as just linking it sideways, okay? I mean, some people kind of don't know when to use equal sign and not to. It's like, come on, right? Okay, so we have 2 limit e approaching infinity, and this is just negative e to the negative xa from 0 to b. And we use plumbing professor, so 2 limit b approaching infinity of, if you put 0, then you get 1 minus e to the negative ba. And then take the limit, so this thing dies. Good. So we have 2. Therefore, this original is convergent as well. You get it? You know what I'm saying? This original integral that from the problem is less than or equal to 2 is what we're saying. Good. Okay, and we'll go to the next problem, which is 46. 46. Okay. We don't really have to do much, because let's just consider this infinite series. Is it obviously infinity? For this thing to have a chance of convergence, convergence meaning some finite number, this thing inside better go down to 0 really, really fast. Even if it goes down to 0, I mean, this may or may not converge. Convergence is not an easy thing to achieve because there are infinitely many of these. Same thing, integral is basically infinite series, isn't it? So this thing better die really, really fast. But take a look at the denominator, right? This e to the something, it does not die. Okay, this thing approaches infinity, but this thing does not. So this is just taking a limit to the left-hand side to see whether this thing dies or not, just to show my work. But I get a feeling exponential function wins. You know what I'm saying? Look at all this vast area. So we don't have to really do a whole lot other than to demonstrate on the left-hand side, this thing approaches infinity. And then area under the infinite height curve is definitely infinity. You get it? So that is the logic behind this problem. How's that? So number 39, what do you want to compare it to? Is the question, right? And then your first thought is this, right? You want to compare it to this thingy. Because from the experience, we know this thing converges nicely. You know what I'm saying? However, this, I think, if my memory serves me correctly, this gives me 1. However, what is the direction of the inequality here? Whoa, what happened? This computer is acting up again. Direction of the inequalities. Oh my God. This way, isn't it? Now, you see the problem with that? That means this integral is greater than or equal to 1. And that greater than equal to includes infinity. So we conclude nothing. So we can't do that, but we don't have any other candidate. You know what I'm saying? So in this case, this is perfect for a limit comparison test. Okay? So I'm going to go ahead and evaluate this integral anyway. So this one will turn out to be limit b approaching infinity r from 1 to b and x negative 2. First thing you write is rewrite it, and then limit b approaching infinity of x to the negative 1, therefore negative here, and 1 to b, and that is limit b approaching infinity, and we use plumbing professor, right? So substitute 1 first, minus 1 over b. You with me? And 1 over b dies, so it gives you 1, as we suspected. Now we have to do the limit comparison test part, which is this. We'll do limit of our given function, which is x square root x plus 1 over x squared over, oh, that's ugly, over 1 over x squared. You get it? As x approaches infinity. And we need to see what that is. Okay. Now, wait a minute, I think I screwed up. I picked the wrong function here, right? Because this thing does not give you finite number. This thing gives you infinity. Do you see that? No, no, no. So I can't do that. I jumped the gun. So I have to pick the better candidate here. Okay, so I take all of this back. I should look at my own note a little more. Okay, so that was a nice try. Now, what can I do then? Well, why don't I compare it to this? Wrong color. Why don't I compare it to this? That was clever. Why would I want to do such a thing? Because this thingy is same thing as, I'm gonna write it out here. This thingy is same as, now I'm gonna write as limit as b approaching infinity of the whole thingy x plus 1, and this is square, and then minus half, isn't it? So do you see this? You know what I'm saying? Do you agree with this rewriting part? Okay, having said that, let's just integrate and see what happens here. So this is same as limit b approaching infinity of, and then this x plus 1, and we subtract 1, so this becomes negative 1/2 power, right? Therefore, put negative 2, and from 1 to b, 1 to b. So far so good. Now I can take 2 out and use plumbing professor. So substituting 1 first, so I have 2 to the negative 1/2 power, which is this. And then minus, if I substitute b, then I have 1 over square root of b plus 1. You with me? And this part dies, so we have 2 over square root 2, which is square root 2. Ah, that is nice, isn't it? Now, then we only need to compare, only thing we have left is compare these two, which is greater. Because if I were to use direct comparison test, then this has to hold. Is it true? And then if you think about it, this is not true now, is it? Because this denominator is bigger than this denominator slightly, so this inequality points that direction. Well, what have we concluded here then? Nothing, right? It's still nothing because your integral is greater than square root 2. So you see, we still have to do limit comparison test now, right? Okay, so let's do the limit comparison test. So go back here. I'm going to zoom in. So our given function, which is square root of x plus 1 over x squared over to the thingy that we are comparing with, which is square root of x plus 1 over and x squared, x plus 1 squared. Like that, eh? Okay, and that thingy, we're simplified to these square root thingies cancel, so you have x squared, x plus 1 squared over x squared. Do you see this thing gives you 1? Right? We can L'Hopitalise it, but can you easily see this is equal to 1? You want me to show you? I think you all see it, right? Okay. Then we can say, therefore, this thingy, our given integral is convergent. You get it? Okay, moving on. So number 40. Okay, number 40. I think we can just integrate number 40. Why? I don't know why we need to do a comparison test. You know what I'm saying? This is easy enough integral, so why don't we just integrate it? So this is equal to limit of, this computer is really, okay, b approaching infinity of, and let's rewrite this from 0. Oh, I see the problem. It starts from 0. So this thing has two different improper parts, this part and that part. You know what I'm saying? So I cannot just put 0 anymore, so let's cut this thing. So I will have a approaching 0. Why does this keep doing this? From the right hand side, and this has to be a now, and 2, let's cut it at 1, shall we? Of x to the negative 1/2 power and dx plus x, and then limit of b approaching infinity, and from 1 to b. How about that? Good. Okay, and then x to the negative 1/2 power and dx. You guys with me? Now, that is equal to limit of a approaching 0, and this thingy becomes x to the 1/2 power, therefore 2, and from a to 1 plus limit of b approaching infinity of, same thing, 2x to the 1/2 power, 1 to b. Now, then substitute a limit of a approaching 0, and I'm going to take 2 to the front. So we have square root 1 minus square root a plus limit of b approaching infinity of, should have taken 2 out as well, limit of b approaching infinity of, now you put in b, so square root b, and then minus 1. So far so good? Now we take the limit. So we have 2 times 1 minus, this thing becomes 0, that one is nice, plus 2 times, we have infinity. Ah, there's your problem, right? So the whole thing becomes infinity. Infinity basically trumps everything. So it's divergent. Good. Okay, any questions before I move on? Okay, number 41 then. Okay, number 41. Wow, what do you want to compare this thing to? Well, let me propose, because that cosine is the only problem we have, isn't it? So why don't I just hide cosine, right? And then we say pi to infinity. First, your initial thought is this, right? Except, what's the direction of inequality here? We can't say, because half of the times cosine fluctuates from positive 1 to negative 1. You see the problem? When it's negative, then like, yeah. So here's a nice adjustment there, right? Because if you think about the graph of this function, it'll fluctuate up and down. This is 2 plus or minus 1. That way we can say, well, then it's definitely this direction, and from experience we know this thing will diverge. Good? You with me? Okay then. Then we rewrite it as limit, as I'm going to put it on the side to save a little space. That is limit b approaching infinity of integral from pi to b 1 over x dx, and that is equal to, I'm gonna save really a lot of space, limit of ln, and we are sure b approaching infinity of pi to b, and now we have limit of b approaching infinity of ln b minus ln pi, and then now you take b to the limit to the infinity, and this thing becomes infinity. How about that? I'm going to move the whole thing over a little bit. Any questions? No? Good? Okay, well then, now we have 44. Okay, 44, what do you want to compare this thing to? Well, why don't I just cover that one up, right? If that one is not there, this is very nice now, isn't it? Okay, And the other thing is this an even function? Yes, it is, right? Okay, but we have a little problem here, because what we want to do is this, right? No, let me just write it. Negative to infinity, and then what we want to do is dx over square root of x to the fourth power. You know what I'm saying? And inequality is definitely in this direction, because denominator is smaller. Now we want to compare this thingy too, right? But this thingy, we have a problem. We have to break this thing up from the middle, except you don't want to put 0 here. Do you see the problem with that? So what we have to do is now this thing is equal to what is the, let me do it this way. This thing, it requires a lot of thinking, but let me, this is the thought pattern. This thingy is from -1 to 1 dx over square root of x to the fourth plus 1 plus 2 times from 1 to infinity of dx over square root of x to the fourth plus 1. Do you agree? I cut the middle part from -1 to +1, and this is definitely positive number. And then this part, I use the symmetry. You want me to draw a little picture for you? Yeah, let's draw a little picture. So what does this thing look like? Let's try to feel it. Oh, that's nice. This computer is just giving me all kinds of trouble today. Okay, now we can zoom in and take a look. Okay, what's the maximum? Really? What's the maximum of this function? It's 1, isn't it? So let's say 1 is somewhere here. And then when we take a limit, x has to, as x approaches infinity, this thing has to be asymptotic, right? It crashed on me. Okay. Hide the ruler. So do you see this kind of behavior? So what I'm doing it is I'm cutting it here at 1 and -1. Okay. Let's go to the side. So this piece is from here to here. You get it? And then this piece is this thingy and that thingy using symmetry. How about that? Do you see they're all there? Okay, then all I have to do is, this is definitely finite number. So all I have to do is just show that this is convergent. You know what I'm saying? So I'm going to do that. So we have this piece from, okay, so we have this thingy from 1 to infinity of dx over square root of x to the fourth plus 1. And I'm going to compare that to this thingy. 1 to infinity of dx over square root of x to the fourth. You see I made the denominator a little smaller. So that inequality holds. But this thingy now is same as, we can write it into proper integral b approaching infinity, and from 1 to b, and that's just all kinds of weird things going on. These buttons are being pressed by themselves. That's just x to the negative 2 dx, isn't it? You with me so far? Okay, then we can integrate, so limit b approaching infinity of, this thing is x to the negative 1 power, therefore negative sign here. With me? Now, then limit of b approaching infinity of, using plumbing professor, I did not write this limit, so 1 minus 1 over b, and that gives you 1. Good. Let's recap. So what do you have? That integral is this piece plus that piece, and that piece is 1. You get it? Where that piece is less than or equal to 1. So this whole thing is less than or equal to 2. And I really don't care whatever this is. That's got to be less than or equal to 2. Just looking at it, right? If you put a rectangle around it. So what we can say now is, therefore, this given integral it changes the color in the middle. Oh my God. It's conversion. I've never seen it do that. Okay, whatever. I think I'm gonna change the color to all of this writing into blue. Okay, good. Okay, and we'll do 45. How much time do we have left in the class?
Technically 2 minutes.
2 minutes?
Yeah.
Okay, is this our last one? Okay, when the 2 minutes it is up, you guys can just leave. I'll just finish this video. Okay, so this one you can just integrate. Okay, let's see how that can be done. So let me first rewrite it. Limit as b approaching infinity and from 0 to b. So far so good. Okay, and then I'm gonna write this, I'm gonna separate these two. So we have 1 plus inverse tangent of y, and then the other part, I'm gonna write dy here, and 1 plus y squared. Now, why would you want to do such a thing, right? Now, okay. Oh, this is my account, okay? Now, what is this, if you think about it, this is the u and that part is the u. You get it? Derivative of inverse tangent happens to be 1 over y squared, isn't it? So we make a u sub. If I let u to be inverse tangent of y, then du happens to be this. Don't have, and then dy. Don't have a time to really show you why that is, but it is. And this computer acting up is not really helping my quest either. Okay, so now then we have limit as b approaching infinity of, we make a substitution, so this thingy is 1 over u. In fact, I'm gonna say u is 1 plus that thingy, because it doesn't make that much difference, but it makes it easier. So what we have is 1 over u and du. Good. Now we have to change the limits of integration. Okay, so when u is equal to 1, u is equal to 0, then you substitute 0 here, right? Do you see this is kind of a headache? U is equal to 0 and 0 here, so inverse tangent of y is equal to -1. You know what I'm saying? Do you wanna keep bring the y back eventually, or do you wanna work with this? Your choice. You have no idea what I'm saying? Okay, if I plug in, let me do that on the side. You guys may leave. If I put 1 here, if u is equal to 0, right, then we have this. That means inverse tangent of y is equal to -1. That means y is equal to tangent -1. You see, that's kind of headache now, isn't it? So what I want to do here is, instead of that headache, I'm going to just bring my y back later. So I'm going to write it like this. I'm going to say y is equal to 0 to y is equal to b. And then I really don't want to do that same calculation with b. Okay, and then I just integrate. So we have limit b approaching infinity of, this is ln, and we are sure. And from y is equal to 0 to y is equal to b, and bring y back. So we have ln of 1 plus inverse tangent of y from 0 to b. Good? You see that's so much better? Now, b approaching infinity of, substitute b, so we have ln 1 plus inverse tangent of b minus, and then you put 0 here, right? Actually, I need to close it, and minus ln 0, so we have ln 1. Good. Now this thing is 0, so it's nice, but this whole thing, inverse tangent of infinity, what is that thing? What is the horizontal asymptote of inverse tangent? May I remind you, inverse tangent looks like this. And that thing is pi over 2, it's not infinity. You get it? So eventually what we get is ln of 1 plus pi over 2. How about that?